All right, so lesson number 1, we're going to start talking about motion, specifically in an area of physics called kinematics, which is how things move. And in this lesson, we're going to be talking about distance and displacement, speed and velocity, how those things are similar, yet they are, in fact, different things. So before we can get into talking about distance and displacement, first we have to talk about position and distance. So we're talking about the motion of objects, how things move. And we can describe that using either words or mathematical quantities or graphs. We're going to talk about all three of those. So to describe an object's motion, first of all, we have to know what its position is. An object's position is its distance away from a reference point. So a reference point is something that is within the frame of reference and has the value of 0, whatever units you're measuring in. 0 miles, 0 meters, 0 kilometers, 0 centimeters, whatever. So again, the reference point is a point within the frame of reference, the field of view, so to speak, that has a value of 0. We can measure an object's distance from a reference point, but that doesn't have a direction. So you could say, for example, I started at the reference point and walked 8 meters. Well, a blind person wouldn't know where to find you then, because they wouldn't know which direction you walked in. So a position, a displacement, a change in position must include a direction. So a position has to include an object's direction from the reference point. So first of all, let's take these red and blue arrows up here, for example. If I wanted to measure, and we're just going to use the dashed green line here. If I wanted to measure this red dot, or this red arrow, excuse me, has a distance of 8 meters from the reference point. It has a position of, there's different ways we can do this. If we put cardinal directions to things, this would be east over here, north up here, south, and west over there. So we could say it's 8 meters east. Or if you look at it in terms of graphs from math class, these would be positive axes and these would be negative axes. So our red, I should have been using red for my writing for this one, but that's okay. I've come this far. The red arrow has a position of positive 8. And I guess I'm considering these, every one of these dots on this dashed line to be meters. Okay, so in that case, the blue arrow over here these are all negatives, of course, has a distance of 6 meters. Notice that with distance, we don't bother putting a positive or a negative or anything, because it's just how far away is it. It's not including a direction. So the distance for the blue arrow is 6 meters from the reference point, but its displacement or position, position would be -6 meters. Or the other way we could do it is 6 meters west. Okay, so there's a difference between distance and position. In that position, we must show which direction from the reference point the object is placed in. When we talk about speed, speed is just a distance covered in a certain amount of time. Okay, velocity is a displacement in a certain amount of time. So what's the difference between distance and displacement? Displacement is an object's change in position from where it started. So let me just get rid of this over here real quick. Okay. And for example, I'm just going to take this red arrow and put it at 4, position of 4 meters, positive 4. Okay. So displacement is a change in position. And we always find change by taking final minus initial. So in terms of symbols, change in position is, we use a delta D for that. And that is found by taking the final position and subtracting the initial position, df minus di. So if this thing starts out at positive 4 and moves to positive 8, starts at positive 4, moves to positive 8, our final position then is 8 meters, and the initial position is 4 meters. So we have a displacement of 4 meters. If instead it starts at 8 meters and moves to 4 meters, so if it starts at 8 and moves to 4, then we still do things the same way, df minus di. This time our df is going to be the 4 meters, and the di is going to be the 8 meters. Technically positive. I get a little lazy and don't write the positives in. So the displacement then is going to be negative 4 meters. Its change in position was negative 4 meters. It went back toward the reference point. Okay? So, same thing could happen with this blue arrow over here. If we move it this way and make it more negative, then it's going to have a negative displacement. If we take it and move it this direction, then it's moving toward the positive area of the graph, which gives it a positive displacement. So, for example, if it starts at negative 6, and moves up to -2, we would take -2 minus -6, and that would be a positive 4 for our answer. Okay? So distance and displacement, two different things. Displacement is an object's change in position. And a position must include a direction from the reference point. And as you just saw, an object can have positive position but negative displacement if it moves from a greater position back toward zero, back toward the reference point. Okay? It can have a negative position and a positive displacement if it moves from a greater negative position back toward the reference point. I threw this GIF in here it's a good illustration of the difference between distance and displacement. So as this black dot moves around this red track, so to speak, you can see it go through this whole thing, and it's moving 10 kilometers, say 10 kilometers east, and then I think it says 10 kilometers, this would be south, perhaps, and then another 10 kilometers east, and then another 10 kilometers south, and then 15 kilometers to the west, and then I believe it was 10 kilometers back to the north, and then finally 5 kilometers to the west. So it moves a total distance of 70 kilometers. But its displacement from its change in position from where it started to where it stopped is only 14 kilometers in whatever direction this would be, some angle southeast. Okay? So displacement is just a measure of where it ends compared to where it started. Okay. So that brings us to the difference between a scalar quantity and a vector quantity. A scalar quantity is something that only has a size, or what we call in physics a magnitude. So distance would only have a magnitude. It's a scalar quantity. A vector quantity is something that includes a magnitude and a direction. So displacement would be a vector quantity. All right, so that brings us to the difference between speed and velocity. So like I said earlier, speed is a displacement, or excuse me, a distance divided by a time. For example, when you say 35 miles per hour, that is a speed. 35 miles would be a distance, an hour would be a time, 35 miles per hour would be putting the distance over the time, and you've got a speed. A velocity has to include a direction. So something like 35 miles per hour east would be a velocity, because that's telling you how fast it's going, the magnitude, and what direction it's traveling in. Okay? So average velocity is technically found by taking the displacement of an object, not the distance that it travels, but its displacement, and dividing by the time interval that it took to have that displacement, to change its position by that much. So an object could move, let's say 10 kilometers to the east, and then turn around and come back 6 kilometers to the west. If we wanted to find its velocity, we would take its change in position, which would only be 4 kilometers to the east. Okay, let's say this happened in, I don't know, 10 seconds. Speed, it moved a total of 16 kilometers in 10 seconds. So its speed would be 1.6 kilometers per second. I just realized I was using kilometers, not meters. So this would be a really fast object to be moving 1.6 kilometers in a second. But we'll go with it. We've come this far. Velocity, on the other hand, would be its change in position, which would only be the 4 kilometers to the east, which we could also call positive 4 kilometers. But the same time interval. So its velocity would only be 0.4 kilometers per second. Okay? So difference between speed and velocity. If you run around a track, one complete circle around a track, that's 400 meters divided by however many seconds it takes you to run around the track. You know, 40 some seconds if you're really good. Heck, I don't know how long it takes to run around the track. It'd take me about 5 minutes probably. But anyway, your speed would be 400 meters divided by however long it took you. Your velocity, though, would be 0, because you go all the way around once, you stop in the same place you start, and that's 0 displacement. Okay? The unit that we're going to be using, for the most part, will be meters per second. We'll be measuring distances. Most of our distances will be in meters, and times will be in seconds. Because displacement is a vector quantity, and we use displacement to calculate velocity, that automatically makes velocity a vector quantity. Velocity has a direction. So, velocity is found by taking the change in position over time. Now, I'm pretty lazy, so we don't usually draw show the triangle in the equation. Triangle is actually the Greek letter delta, which is a triangle shape. And in science, that means change. But, again, I'm kind of lazy, so we usually just leave the triangle part out of the equation. And we have v is equal to d over t. Okay? That can be rearranged to find t. It can be rearranged to find d, depending on what you have to work with and what they're asking you to find. All right? We multiply both sides by t. Then d is equal to v times t. Then we could divide both sides by v to leave t by itself. And t would equal d divided by v. I'll put that other one back up here. D equals v times t. Okay? If you like these things, you'd have d on top and v and t on the bottom. So if the average velocity is the same for all time intervals, then we say that the object is moving with a constant velocity. It's covering the same, let me rephrase that, it's having the same displacement, moving the same amount for every time interval. As we said before, we can display an object's motion using a graph. We can use words. The object is traveling at 15 meters per second. We can use an equation, like the one I just showed you. We can calculate the object's velocity. And we can also show with a graph. We're going to be looking first at what's called a position time graph. It's called a position time graph because it puts position on the y-axis, that's the dependent variable, and time on the x-axis, which would be the independent variable. Time is always an independent variable. Everything else depends on how much time has taken place, or how much time has elapsed. All right? So position time graph. Look at this graph, right? Hopefully you guys have seen that Vine before. So here's a position time graph showing you the motion of these two cars. The blue car starts out at a position of 20, and so on the graph it starts out with the y-intercept of 20. And then it's moving at whatever speed not very fast, relatively speaking, relative to the red car. The red car starts out back here at 0, but we don't see it on the timer until the timer has reached 4 seconds, so that's why it starts here. Okay? But it's moving much faster, so it has a steeper slope. And at this point, right there, is where the red car passes the blue car, which takes place at about, looks like about a little after 7 seconds and right around 70 meters. Okay? We can tell that the red car is traveling faster than the blue car because it has a steeper slope on the graph. The steeper the slope is, the more position is being changed per second, and that means it's moving faster. Okay, so we have a position time graph here. On a position time graph, we could calculate the slopes, and the slope, if we look at the equation, slope is delta y over delta x. So on a position time graph, slope would be equal to the y-axis is displacement, so we'd have delta d, and the x-axis is time, so we'd have t. So slope is delta y over delta x, which is d over t, and that means that the slope is equal to the average velocity of the car, or whatever object we're graphing. Okay, so the slope of any section on position time graph shows us the average velocity for that time interval, which I will leave you with this right here, which shows you, it changes the section of the graph that we're looking at. So right here, if we're looking at point A to point B, we would have a positive slope. So from point A to point B, it has a positive average velocity. If we continue to let the timer run until the object reaches point D, well, now its change in position is negative because it starts over here at 30, and at point D, it's back down to 0. And so we'd have a negative 30 for the change in position over 30 seconds for the change in time, going from 0 to 30 seconds. So negative 30 divided by 30, we would have, so from point A to point D, we'd have negative 30 for the change in position and 30 seconds for the change in time. So we'd have an average velocity of negative 1 meter per second. Point A to point B, we'll do it in a different color. We'd have a change in position of 30 up to, looks like 50. We'll just call it 50. So from 30 up to 50 is a positive 20. So you take 50 minus 30. And that happened in 10 seconds. So for section, to go from point A to point B on the graph here, 20 meter displacement divided by 10 seconds, it would have a positive 2 meter per second average velocity. Okay? All right, so we'll leave it with that, and we will look at some example problems and whatnot in class tomorrow. All right? We'll see you.